Hello, hello. I'm going to show you how to do a gas laws problem. So in this problem we've got acetylene gas, which is C2H2. It's used for welding. In fact, if any of you have ever taken a metal shop class, which I highly recommend, you will probably learn how to use acetylene gas in welding. Well, in any case, imagine we've got a 5-liter tank that is stored at negative 23 degrees Celsius, and it's at a pressure of 5 times atmospheric pressure. We want to know what temperature would that same amount of gas be at if it was in a 10-liter container with 2 atmospheres of pressure. So there's really only one equation that you need to know, which is the ideal gas equation. And it says that the pressure times volume is equal to the number of moles, that's N, times the ideal gas constant, R, times the temperature, T. Keep in mind, and this is a mistake a lot of people make, the temperature must be in Kelvin. And of course you can see here that our temperature is not in Kelvin, it's in degrees Celsius. So we're going to have to change that. But first, I want to figure out what part of this equation is going to stay constant regardless of when we move the gas to a new tank. So I know that the number of moles is going to stay constant because we're not going to be letting any air out of the tank, and we're not putting any more air into the tank. The same number of gas moles is what we have in tank 1 and in tank 2. Another thing that's going to stay constant is the ideal gas law. That's just a universal constant. It's true for all ideal gases everywhere, ever, period. Now the stuff that's not going to stay the same, the stuff that's going to change when we put our gas into a new container, is of course the pressure. Remember, we had it initially stored at 5 atmospheres, and it's going to end up at 2 atmospheres of pressure. So pressure is definitely changing. Another thing that's going to change is the volume. This 5 liters of gas is going to be in a 10-liter container, and you can bet the gas is going to spread up and take up all of those 10 liters of space. So pressure and volume are going to change. And lastly, the temperature is also going to change. Remember, in the first tank it's going to be at negative 23 degrees Celsius, but in the new tank we're trying to find what the temperature is going to be when it's under new pressure and it has a new volume. So here's how I'm going to solve this. I'm going to start by moving all of the things that will change over to one side of the equation. So divide both sides of the equation by T, and then this gives you PV equals T. PV divided by T equals N times R. So now everything on the right side of the equation is constant. And that's exactly how it should be. Because that same amount that's on the right side of the equation, well, it's still going to be constant when we have our gas in a new tank with a new pressure and a new volume at a new temperature. And so you can see these two are equal, which means that these two are equal as well. So I'm just going to go ahead and cut out the middleman, and I'm going to set up my equation as PV1 over T1 equals PV2 over T2. And so now the question is, what is P1, V1, T1? Well, what stuff can I plug in? So for pressure 1, it says that we are at, what is it, 5 atmospheres. Okay, so 5 atmospheres is pressure 1. Volume 1 was 5 liters. Temperature 1 was negative 23 Celsius. Hold on a second. What units does temperature have to be in? Oh, that's right, Kelvin. So I'm going to take this temperature and convert it to Kelvin. It's 273 plus the degrees Celsius, which in this case is negative 23. And when you do that, you find that the temperature in Kelvin is 250 Kelvin. Not degrees Kelvin, Kelvin. So 250 Kelvin is what I'm plugging in. Okay. Next thing is P2. What's the new pressure going to be? Well, it says 2 atmospheres in this new tank. And the new tank is going to be 10 liters of space. And I want to figure out what's the temperature going to be. So solve for T2. Now, you're going to be tempted to take all this stuff and move it over to the other side of the equation by dividing, but that's not going to give you T2. That's going to give you 1 over T2. And that's not what we're looking for. We don't want to find the reciprocal of T2. We want to find out what T2 actually is. So you have to multiply both sides of the equation by T2. And then, to get T2 by itself, you're going to have to divide everything on this side. You're going to have to divide it through both sides of the equation. So, at the end of the day, what we get is 2 times 10 times 250 divided by 5 times 5. And that is, let's see, 2,500, 5,000 divided by 25. And when I punch that in, we get a final temperature of 200 Kelvin. But hold on a second, the units for temperature were given to us in Celsius, so we should do our due diligence and convert this to Celsius. And to do that, we've got to subtract 273. And what that gives us is negative 73 degrees Celsius. And that is our answer. I want to point out one quick thing, which is that it makes sense that our new temperature, negative 73 degrees Celsius, is colder than the original temperature. That makes sense because our gas is now taking up a larger amount of space and also with less pressure. Less pressure, more volume, the temperature is going to be a bit lower. It just happens with the numbers that we've got here. So when a gas expands, you would expect it to get cooler. And that's how you solve this problem.